Okay, I think this is working. Make sure. Yeah. And so since we have an absolute zero for entropy, we can calculate changes in entropy by delta S. Delta S is just the entropy of the products minus entropy of the reactants, whatever it is. S final minus S initial. So we just sum up all the products, sum up all products. Entropy also depends on the amount. So for example, if we have 1 mole versus 2 moles, then 2 moles of entropy will be higher than actually double that of 1 mole. And this would be the sum of all the reactants. But this has an absolute zero, and the absolute zero of entropy is this. Unless, of course, we're looking at, if we're looking at ions, you can't form a cation without an anion. And so the same thing happens with entropy here. So same situation arises with entropy, in which we have to have an arbitrary zero because we'll have 2 unknowns and 1 equation. And so here, 1/2 hydrogen, the entropy for this is 0. Or is it? No, it's not 0 because it's a hydrogen gas. And gases have entropies around what? Gases have entropies around what values? Solids have entropies around what values? Did anybody write it down? It's easier to remember if you write it down, and then you can review it. But you don't write it down then. 0 to 100. Liquids, this is very easy. 0 to 100 for solids. Liquids, 100 to 200. And gases, well, 200 plus. 200 plus. This is a lower entropy gas, so, we don't expect it to be much beyond that because this is just a diatomic. So maybe about 200 kilojoules per mole. And then half of chlorine, same thing with chlorine. It's pretty lower entropy for a gas because the molecule, the more complex the molecule is, the higher the entropy because you got a lot of different kinds of vibrations and that kind of stuff. And then HCl here. And so we can do like calorimetry type things or whatever and figure out the entropy of this particular thing, but how much of this is due to the formation of the H plus and how much of this is due to the formation of chloride? Because we're forming H plus and the chloride, and you can't separate that, so we have the same situation arises. So it's a 2 unknown problem here again. I'll just use different variables for this, so we'll call this W here, and this one's Z. W plus Z. We know what the sum total is here. This can be determined. And so one of these is arbitrarily set to 0. Which one is arbitrarily set to 0? So arbitrary 0. This is what you need to go back through the notes, There's not enough time to put in all the details here. This is also going to be an arbitrary 0 rather than absolute 0. Arbitrary 0. Here. And so if there's 2 unknowns, but only 1 equation, then we'll just set 1 to 0. The units are different here. In delta H is always kilojoules per mole. The units for this are joules per mole Kelvin. Joules per mole Kelvin, the units for entropy. Well, this turns out to be easy. What we do at 298, this is easy. At 298, the data is in Appendix D. And so it's just simple addition and subtraction for Appendix D, multiplication, depending on how many moles we have. That's it. So we can determine entropy changes quantitatively, and it's not too difficult to determine those entropy changes. Like, for example, this delta S for this is going to be the entropy of the HCl. Now, the appendix D is also under standard conditions, so we have to be under standard conditions here. Minus the entropy of 1/2 the entropy of hydrogen gas, under standard conditions. Plus, it's the sum of the reactants, plus 1/2 the entropy of the chlorine gas. So we just need to go to Appendix D, look these values up, and then that's it, basically. Get back in. To the text. Oh, why so many clicks just to open the textbook? So scroll down here. We got to look for HCl. So that's under probably hydrogen, the element hydrogen, or the element chlorine. It's not under chlorine, so let's take a look under hydrogen here. Okay, we have two choices, HCl gas or HCl aqueous. We're going to go with HCl aqueous. And entropy, the absolute entropy for HCl aqueous is 56.5. 56.5. Okay. So that's easy enough. Units, joules per mole Kelvin. Now, this is 1 mole. And so technically I have it 1 mole. This is actually 1/2 refers to 1/2 mole here. And this is 1/2 mole. Even though, and so I'm just going to get rid of the per mole here. I'm just going to call it joules per Kelvin. Okay, but minus 1/2 mole times the hydrogen gas entropy. So looking at the hydrogen gas entropy, what is that? That's going to be under hydrogen here. Hydrogen gas entropy is pretty low. It's 130.7, quite low. So it's pretty low entropy gas. So we'll go back here, 130.7 for hydrogen, but we only have 1/2 mole. And so we'll only have half that entropy. Energies are extensive properties versus intensive properties. And so this is going to be 1/2, 130.7 joules per Kelvin. The moles cancel out. Plus 1/2 mole of chlorine gas. Let's see what the entropy for chlorine gas. Chlorine is also, I'd expect it to be kind of low entropy for a gas. But look, it's a bit higher. Do you see that? 223.1. Well, hydrogen is very small, simple atom compared to chlorine, which is a bigger atom. It must have something to do with it. 223.1. So go back here. Okay, come on. So hard to see this little tiny dot. 1/2, 230.1 joules per Kelvin. All right, so now we can calculate it, what the entropy change for this is. This one's a tricky one to predict, but I think the entropy would go down, wouldn't you? Because we're going from gases to aqueous solution. So it seems as if the entropy should be going down and come out negative. And so I kind of think that's going to happen. So I'm going to do the parentheses first. So 0.5 times 130.7 plus 0.5 times 230.1. So 180.4, 54, 56.5, negative 123.9. It's kind of what we expect because gases have higher entropy, liquids have lower entropy. It's 123.9 joules per Kelvin. This is for this reaction is written. And so what this is for reaction as written. What that means is we could use this as a conversion factor. And so this would be, in other words, for the reaction as written would be per 1/2 mole of H2 reacting, per 1/2 mole of Cl2 reacting, and per 1 mole of HCl being formed. And so if we wanted to use this as a conversion factor, this would be per 0.5 moles of hydrogen, or per 0.5 moles of chlorine, or per 1 mole of HCl. And therefore, if I write joules per mole Kelvin, I have to specify what moles I'm talking about. Am I talking about H plus? Am I talking about Cl2, or I'm talking about HCl? And so it's just easiest just to leave off the moles and have it as the reaction is written. So this is by far the easiest way to determine delta S, as long as the information is in the Appendix D. But there are other ways of determining delta S. From the Clausius, let's recall that, delta S is equal to Q over T. The Q reversible, there's a restriction on the heat. It can't be an irreversible exchange of heat. In order to do this reversibly, it has to happen infinitesimally slow, and it can go either way. And so this is at the ultimate limit because, when we think about heat, it doesn't happen infinitely slow and reversible in time. But this would be it. There are things that do happen reversibly, and that is when we're at equilibrium, it happens reversibly, right? And so at equilibrium, the forward and the reverse process are happening. And so we use this equation to do different things. So for example, we use this equation to determine absolute entropies, right? And so we did this for the experimental determination of S, S final, as above, talked about earlier. That's one way we use this equation. Another way we use this equation is for phase transitions. Phase transitions were under reversible conditions, because of phase transitions, we have an equilibrium between different phases, like solid to liquid and melting. Phase transitions would be like melting. Melting has a different name that's typically used. What is it? It's called fusion. What's the opposite of melting? The opposite of melting is freezing, etc. So under phase transitions, this gives us an alternate way of determining this, delta S. Delta S of the phase transition is just equal to Q. The heat exchange is going to be delta H. So this is going to be delta H of the transition over the temperature of the transition. The temperature of the transition would be the melting point, the freezing point, the boiling point, the condensation point, etc. And so this gives us a way of determining delta S. There's a rule that some people use. And this rule is this. It's not a law, but if I'm going from a liquid, liquids have entropies of about what? You say 100 to 200. If I'm going from a liquid to a gas, the gases have entropies like 200 to 300 or something like that. Then delta S of vaporization is going to be approximately what? So anyway, we could calculate it. The calculation's easy enough. This is a straightforward calculation. But sometimes people use these rules when the data is not available. What types of things do people calculate here? I'll talk about the rule in a second, but we either calculate delta S or delta H or temperature. You know, so sometimes people will calculate the boiling point. You know, example, temperature of the boiling point. The temperature of the boiling point is just equal to delta H over delta S. The units work out, you know, because delta H is the units actually don't work out here, because what are the typical units of delta H? They kind of work out, they kind of don't work out. And what I mean by that is delta H is typically in units of kilojoules per mole. And delta S is typically in units of joules per mole Kelvin. The per mole cancels, but the kilojoules and joules don't cancel. So what we have to do is we have to multiply this by a conversion factor, 1,000 joules per kilojoule. Otherwise it doesn't work. There are some people, I don't know, still in Chem 1B who don't use units in their calculations. And it's almost hard to believe that they get this calculation wrong, because it should be a straightforward calculation. But if you don't have units, then it doesn't really work, because they just take the delta H from the table and the delta S, and then they just plug it in there, expecting it to work. Sometimes we use a rule. The rule is that the delta S of vaporization should be, you know, gases, which are about, let's say, 200, and liquids, which are about 100. So gas, 200 minus liquid, 100, gives us delta of S about 100, right? Joules per Kelvin. What they did was they looked at the data and were able to narrow it down even more precisely, because, you know, a lot of liquids kind of have the same entropy. A lot of gases have pretty much the same entropy. So this rule, and in fact, sometimes I don't even talk about this rule because I don't see the utility of this rule that much, but maybe I just don't do enough thermodynamics to see the utility of this rule. But then I was looking at some standardized tests and they talked about this rule, so I thought, I guess some people think it's quite important. What happened there? I guess it didn't quite copy the whole thing. And so, you know, these people who did this rule, they looked at a whole bunch of data, and then they were able to more precisely define it. But the problem with that is there are a number of exceptions that they kind of expect you to just know the direction of that exception. And so let's take a look. delta S. And they were able to pinpoint it to a lot narrower temperature range. Like we say about 100, which makes sense, you know. That would be like this, jump here. That would be about 100. Do you see that? And the liquids we expect to be about 100, but you know, the difference in entropy between solid and liquid is a little bit less. But it's still roughly around 100. This is not very precise, right? We expect the entropies to increase. This is a chart of entropies. The chart I had drawn was not entropies. Do you know what I had on the chart I drew? The chart I drew when talking about how they measure, how absolute entropies are measured from molar heat capacities. For the molar heat capacity, the molar heat capacity of gas is lower than a liquid. And so what we're looking at is we're looking at integrating, that is summing the area, and therefore the gas is going to be higher because we're summing from 0 all the way up to the gas. So the gas is going to have the highest entropy here. These are the phase transitions here, these vertical lines. The phase liquid to gas, solid to liquid, phase transitions. Some gases have higher entropy, some gases have lower entropy. The higher entropy gases are going to have more complex vibrations. These are called vibrational modes. This is for water. There are 3 vibrational modes. They have names for these. These are quantized in terms of energy. So water doesn't absorb all energies of heat. Water only absorbs the energies of heat that can cause these vibrations here and rotation. Microwaves are extremely efficient because microwaves are tuned, that is, they're tuned that they have the correct energy to rotate these water molecules and increase the kinetic energy. That way we don't waste a lot of energy. A lot of energy is not absorbed because it doesn't cause anything to happen. It's quantized. So microwaves are very efficient. A stovetop isn't. A stovetop, you're blasting all energies of heat, the entire spectrum of heat on there. But only 3, when you look at the infrared spectrum of water, there are only 3 bands that absorb, and everything else is just passing through, not being absorbed. So it's very hard to tune a flame. If you could tune the flame to only have 1 energy or 3 energies corresponding to these 3 vibrations, it'd be perfect. Here we can see NO versus NO2. NO2 has more ways of arranging things, you know, because it has 3 vibrational modes like water, whereas NO only has 1 vibrational mode here. And so NO2 is going to have a higher entropy than NO. Methane is going to have pretty high entropy as well, although that doesn't look terribly high, 186. But compared to ethane, ethane has higher entropy because it's more complex, has more vibrational modes. Propane, higher entropy yet. But they're still all hovering around where gases, you'd expect gases to be. But you know, there's some overlap here. You know, the amount of energy stored, you know, how many ways. The water is a great heat sink. And so here you can see a correlation between that heat sink and entropy. And this is why we can use heat capacities to measure these types of things. So let's take a look at here. Well, actually, I don't want to spend too much time. I don't want to spend too much time on this. But this rule here is they've narrowed it down. And I think it was narrowed down to about 87. And so delta S of vaporization is about 87 joules per mole Kelvin. Unless you have a specially ordered liquid, like water, well-ordered liquid, then the entropy change is larger. Well-ordered has different meanings, Liquids are inherently disordered, but there's some order to it. Because the hydrogen bonding interactions have to be maximized. And then it's greater than 87. So why do you want to measure, use this rule? It's for certain things, like if there's no thermodynamic data, let's say appendix D is lacking the data, then we could use this perhaps to do calculations. And so the utility for us is not so high. Most of the stuff we're going to be dealing with is in appendix D.
Sorry, can you really quickly just re-explain the unless well-ordered?
Well-ordered liquid. All right, this delta S, this rule is for delta S of vaporization around 87, 89 joules per mole Kelvin. For the typical vaporization, the typical liquid going to typical gas. But if you have strong, let's say, hydrogen bonding interactions in liquid, that keeps the liquid more ordered than normal. And if the liquid's more ordered than normal, like if you look at liquid water, it has a very low entropy compared. What do you expect for the entropy of water? Do you guys remember this from yesterday? Or not yesterday, the day before yesterday? We expect, it's a liquid, so we expected 100 to 200, right? What was the entropy for water? Did anybody write it down? It was quite low. It was like 60s, in the 60s, right? In fact, let's just look at it again. And so this would be a deviation from the rule. And therefore, if you have a rule that you have to memorize a lot of deviations for, although this one's not too terrible to memorize, because there are reasons why it is. If you look at H2O liquid, H2O liquid is a well-ordered liquid because look at the entropy. The entropy is quite low, 69.91. This comes from, how do you do this? How you do this is you look at the numbers. What we do is we look for the largest entropy, this is what I do. When I have a table, I look for the smallest value, and I look for the largest value, and then I look for some kind of mean, and I look for kind of distribution around that mean. Does that make sense? And so we look, and then you go into finer detail. Okay, then we look at all the solids. What's the largest entropy? What's the smallest entropy for all the solids? And go to the liquids, and then go to the gases. And then you can get more comfortable with the numbers. So I'm not going to do that because we have limited time. Normally I'd do that. Instead, I'll just tell you roughly what they are, but it's not so precise, In fact, like I said, this rule, I don't normally even bother with this rule, but I saw it in the standardized test, and I thought, okay, I skipped this rule normally, but it appeared on the standardized test, so I better talk about it because somebody thinks it's important, I just didn't think it very important. And there's actually a name for the rule. You could look up the name in the book if you want to know the name for the rule. It's called Troughton's rule. But that's another way we use this, Clausius. And then there's one more way we use this. And this is a very powerful way. We use this, not this. Go back up. We use this. This is probably one of the biggest applications. We use this to determine delta S of delta S of the surroundings, which is pretty much the rest of the universe other than the system. And so this is a key application of this equation. We use this to determine delta S of the surroundings. Delta S of the surroundings is the rest of the universe. Do you think Appendix D is comprehensive enough to contain the rest of the universe? Are we going to find the data? And anyway, do you want to catalog everything in the rest of the universe and then calculate delta S? Even though the delta S calculation is very simple, we need the data in Appendix D. Are we going to have it? No. And so this is one of the most powerful uses of this equation here. One of the most powerful uses is to figure this out, because I know the second law of thermodynamics. The second law of thermodynamics is this. The second law of thermodynamics states that delta S of the universe has to be greater than 0 This has to be greater than 0 for a spontaneous process. That spontaneous has a driving force. So we need a driving force. We need delta S to be greater than 0. That's our driving force. Delta S of the system is easy to calculate as long as it's in Appendix D. But what about the delta S of the surroundings? Delta S of the surroundings is pretty much impossible to calculate, right? It's pretty much impossible to calculate because Appendix D doesn't contain everything in the rest of the universe. But we're very lucky. And so we'll talk about this now. So what we want is we want to be able to use the second law of thermodynamics. So let's take a look at the second law again, thermodynamics. And the second law is that delta S of the universe needs to be greater than 0 in order to have driving force, a spontaneous process. If it's equal to 0 or less than 0, there's no driving force for the forward. If it's equal to 0, it's at equilibrium. That is, there's no change. Equilibrium. If it's less than 0, then the driving force is for the reverse reaction. Reverse reaction favored. But we need to quantitate it. So there are two things we could do. We could do this qualitatively, or we could do this quantitatively. So, but qualitatively, it's too impossible. Because how do we know if the entropy of the universe is increased or not? Because, well, the system's easy, like I said. The problem is with the surroundings. So delta S of the universe is equal to delta S of the system, all right, plus delta S of the surroundings. All right. And so delta S of the system we're going to leave as is, because delta S of the system is manageable. We have two types of systems that we look at. One is what, and the other is what. This is manageable. Because we're either talking about heating or cooling an object. So object, or we're looking at a reaction. So that's totally manageable. But delta S of the surroundings is not. And so what we do is we'll just say delta S of the surroundings is equal to Q reversible of the surroundings over T. That's what we'll do. But the interesting thing about heat is the first law of thermodynamics. What does the first law of thermodynamics say? That energy is neither created nor destroyed. And so if the surroundings gains or loses heat, it doesn't disappear. If the surroundings gains or loses heat, where did it come from or where did it go? The system. So we know this. We know from the first law of thermodynamics this is one way. There's lots of ways of writing the first law. Q of the surroundings is equal to minus Q of the system. So if the surroundings is negative, the system is positive. If the surroundings is positive, the system is negative. The negative just means opposite sign. It does not mean exothermic. It just means change the sign. And so this is going to simplify into delta S of the system plus a minus Q reversible of the system over T. The next thing is this. The problem with Q is it's what we call a path-dependent function. What's the problem with a path-dependent function versus a state function? Somebody remind me that. That's Chem 1A. This is why so many people fail thermodynamics, is because it's so easy to forget this stuff. I was up at where was I up at? I was up at this transfer. So I went up to Berkeley Saturday, and I was listening to, this was an engineering transfer, and I was listening to some of the engineering transfer students there. And one of them was talking about thermodynamics. You know, she transferred and she was taking thermodynamics. So it was a very, brutal course, but everybody has to take it. And so she was giving advice to the transferring students. And I thought, oh, that's good advice. 'Cause thermodynamics is known for high failure rate. But lots of people have to take thermodynamics. Even biologists have to take thermodynamics, the ones that are interested in energy, bioenergetics, which is, of course, important because you need energy for life. So I was watching this other YouTube about mitochondria, talking about mitochondria does much more than just energy. This is why all that red light therapy and other stuff they're talking about. It's interesting. But anyway, it's like you forget this stuff. And you forget this stuff, and then you're expected to have known it. But Q is a path-dependent function. What that means is the amount of heat you get depends on how you do the reaction. What we need to do is we need to make Q a state function. A state function means the amount of heat you get is always the same regardless. Well, I shouldn't say regardless, because we put some restrictions to make Q always the same. You know what restrictions we put to make Q the same? In other words, this is one of the major topics in Chapter 7. One of the absolute major topics in Chapter 7 was making Q a state function. In fact, I'd say this is the number one topic of Chapter 7. How to make Q a state function. How we make Q a state function is we restrict the pressure to constant pressure, and we restrict the work to P delta V work only. By doing these two restrictions, then Q is always going to be the same. This is Q changes depending on what. Q always the same. And we call it a state function. And then we give it a new name. Since Q is a state function, we call it something else to differentiate it from a normal Q, because we don't want to get the Q as a state function and Q as a path-dependent function mixed up. So do you know what symbol we give Q as a state function? Uh-huh. Little circle just means standard conditions. That little circle means you're at 1 bar or 1 atmosphere pressure and 1 molar concentrations. It's under standard thermodynamic conditions. It doesn't tell you if it's a state function or whatnot. Do you know what symbol we give Q when we make it a state function? Giselle, you remember? Delta H. That's why this is the major topic in chapter 7. Making Q a state function. All right, so what we're going to do is we're going to do the same thing here. We're going to restrict this. So delta S of the universe is equal to delta S of the system plus the minus Q of the system. I'm going to get rid of the reversible. It's there, but over T. And then we restrict it. We restrict it to constant pressure and PV work. Well, that's the normal restriction. When we're doing delta H, that's the normal restriction that we have. Delta H doesn't work for everything. If you try to use a bomb calorimeter and you call that delta H, sometimes you get lucky. You know, when delta N of gas is 0, then delta H and delta U are the same thing. But if you use delta H blindly and use it for bomb calorimetry, you're going to be wrong sometimes. You know? So you have to be careful. Constant pressure and PV work, P delta V work. I can call it minus P delta V work because that's a system. It's usually minus P delta V. And so this is equal to delta H, delta S of the system, okay, minus, okay, I'm going to put in delta H instead of Q, and we'll just call it delta S of the system over T. And then, I don't know why they do this, but we're going to multiply this by T. So we're going to get T delta S of the universe is equal to, actually, I'm going to multiply by minus T delta S of the universe. Minus T. Minus T delta S of the universe is equal to delta H of the system. Okay, now delta S is going to be negative, and it's going to be multiplied by T. So this is going to be minus T delta S of the system. And so this is a new state function. Delta H of the system is a state function. T is a state function. Delta S of the system is a state function. So this is a new state function. And this is going to be defined as delta G. And so the second law is just typically stated in terms of delta G. This is the change in Gibbs free energy. Gibbs is a professor at Berkeley, very famous in thermodynamics. I was there. I didn't go to Berkeley, but I was there at the chemistry department. They have a picture of Gibbs there. Change in Gibbs free energy. The free energy, Gibbs, this is just the absolute free energy. We call this absolute free energy, which is just G. G is not calculated because the absolute enthalpy is not determined. So this is minus TS. The absolute entropy is not a problem. This is the problem here. And so we don't usually use, so delta G is not a G final minus G initial type thing. Usually, and so it's kind of, there is one thing that's similar, and that is Hess's law. So when we do delta G, it's not a G final minus G initial thing because of this. Not determined. S is determined. There's no problem with S. H is the problem. H is the problem because of the potential energy term. Actually, this is also from Chem 1A. What is H equal to? Here. H is equal to U plus PV. And so it's just the total energy with this PV. And the PV comes from the interaction of the system and the surroundings. So this is the problem here. These are state functions here. This is the problem with this is the potential energy term. The kinetic energy term is easy, but the potential energy term is difficult. And therefore, if U is not determined, H is not determined either. And so this is not normally done here. Instead, what we do is we do this. And so an increase in entropy of the universe results in a decrease in delta G. So if delta G is less than 0, then we have driving force. It's spontaneous. If delta G is equal to 0, then it's at equilibrium. If delta G is greater than 0, then the reverse reaction is favored, reverse favored. And so we have to flip our thinking now. We want a decrease in this, and it's a decrease in the Gibbs free energy is what we're looking for. And so ultimately, the second law can be summarized with this equation, that delta G of the system, whatever, is equal to delta H minus T delta S of the system. These are all in terms of the system. Now, delta S of the system is easy. You know, what's the easiest way of calculating delta S H of the system? Well, let's do this qualitatively first. Qualitative, we look at delta H. And then we look at delta S, and then we look at delta G. If delta H goes down, i.e. it's negative, less than 0, and delta S is positive, then that's always favored. Then delta G is negative at all temperatures. So this is spontaneous. We say it's spontaneous at all temperatures. However, if delta H is positive and delta S is negative, that is, this is always going to be positive, then delta G is positive at all temperatures. And so this would be non-spontaneous at all temperatures. And so this is where we come up with nature wants to minimize energy. Minimizing energy is decreasing delta H and maximizing entropy. So this is favored here. We're minimizing energy. Maximize entropy. And that's favored. Here we're not minimizing energy, we're maximizing. And over here we're not maximizing entropy, we're minimizing entropy. So that's going to be unfavored at all temperatures. The problem comes about when you have a conflict. One says yes, the other says no. And so for example, the energy might say yes, minimize energy, but the entropy might be no. And so this is a yes, no. What's the answer? Yes, no. Well, the answer is going to be yes or no. And it turns out it's depends. Depends on which term is bigger. Which term is bigger is going to depend on the temperature. And so we end up with two answers for this. The two answers is it's yes at low temperature. It's no at high temperature. And so we say that this is spontaneous at low temperature, non-spontaneous at high temperature. High temperatures favor the entropy term. So if the entropy term is saying no, then high temperatures is going to magnify that. So. And then let's say the energy says no. So the energy says no, but the entropy says yes. Then the opposite thing happens. So this turns out to be non-spontaneous at low temperature. But, you know, the entropy is saying yes, then it's going to be spontaneous at high temperature. And this is just, you know, when we get some numbers here, then it makes more sense. So this is qualitative, so we don't have numbers there. And so this is all we can say, basically, when these scenarios. Some of the reactions we can just look, you know, is it exothermic? Is it endothermic? You know, is the entropy going up? Is the entropy going down? So some reactions is pretty easy to determine, you know, if it's going up or down in terms of energy and entropy. So let's take a look at some reactions that are easy to determine here. Some of these might be difficult to determine delta H, but I think we can determine it. Let's take a look at the energy. Calcium oxide and water forms calcium hydroxide. When you look at that, what type of reaction does that look like? This kind of looks like just I could classify this as a Bronsted acid base, or I could classify this as a Lewis acid base reaction, because oxide's a powerful base. However, it's not so powerful when it's locked in a lattice like this, but oxide itself is a powerful base, and this is plucking protons off water. So oxide's the base, water is the acid, we're forming hydroxide. So what's the stronger base, oxide or hydroxide? Oxide, so this has got to be exothermic, right? So this is what's happening here is the enthalpy is saying going down in enthalpy and energy. But what's the entropy saying? Do you think the entropy is going up or going down? Well, we're going from a solid and a liquid to a solid. So what do you think is happening with the entropy? It's going down. So the entropy is saying no, energy is saying yes. So we'd expect this to be spontaneous at low temperature, non-spontaneous at high temperature. Let's go on to B here. Here, B, there are different ways of thinking about this here. This one's kind of tough because mercury, you know, mercury is kind of like a Nobel metal. It's pretty unreactive, like gold, you know, platinum. Although it causes damage to your brain, you know, breathing mercury vapors, which I probably have breathed in lots of mercury vapors because ever since I was a student, there have been always broken mercury thermometers in the lab. But anyway, so I don't know, is this endothermic? Normally I'd say this is endothermic because we're breaking bonds. And so I'd say this is endothermic, most likely. When we form bonds, it's exothermic. When we break bonds, like if you break a stick, does it cost you energy? Yes, it costs you energy to break a stick. So breaking bonds costs energy. And so most likely this is endothermic, but you know, some things don't like to form bonds, like gold. Does gold like to form bonds? And so there, it's backwards from what we typically think, because forming bonds with gold is unfavorable energetically, you know. So anyway, this one's more tricky, but the entropy is easy. What's the entropy? Entropy is going up or down? Up. This one should be easier, you know. What's more stable, salt or sodium metal and chlorine gas? What would you rather sprinkle on your French fries, salt or sodium metal and chlorine gas? Salt. Yeah, salt's more stable. So this has got to be endothermic, right? We're going up in energy. Well, it's endothermic is not favorable, but the entropy is also going up, right? And so we'd expect this to be spontaneous at high temperature. And so very high temperatures, it's going to take some extreme temperatures, because I've tried to melt salt on a frying pan and I wasn't able to melt it. And no matter how long it sat on the frying pan, it sat like 1 hour on the frying pan, it didn't melt. But the hot salt you can use for different things. You know. Anyway, this has got to be pretty high temperatures. Well, how high of a temperature? At what point will my salt not just melt, it'll decompose into sodium metal and chlorine gas? You know, what temperature we'd like to know that. And so these are the types of things we can calculate using thermodynamics. You want to know. Well, what's happening with the entropy here? What's happening with the entropy here is a solid and 3 moles of gas going to a solid and 3 moles of gas. Now we have 1 mole of solid, but this is a more complex solid, and we have 2 moles of solid here. So 2 moles of solid usually has more entropy, but this is simpler solid that's more complex solid. So I say the entropy didn't change much. Although carbon dioxide has more complex vibrations than carbon monoxide. So the entropy of this gas is a little higher. And so there's going to be a slight change. So the entropy kind of goes down with this and kind of goes up with that. And so I'd say it's a break even. And so I don't think much happens here in terms of delta S. Here, this is going from solid and 2 moles of gas to 1 mole of gas, but this 1 mole of gas is much more complex. You know, silicon tetrachloride is a tetrahedral molecule and has more vibrational modes than chlorine. Chlorine just has 1 vibrational mode, which is like this, but this has 3 vibrational, is it 4 vibrational modes? I don't remember. Uh-huh.
Sorry, can you repeat? Can you go with A one more time?
A?
Yeah.
A in terms of entropy, entropy goes down because we have a liquid and it's being replaced with gas. So entropy goes down. Enthalpy for this should be exothermic because we're going from stronger base to weaker base. They're not asking for enthalpy though. This is doing it for additional practice. I think they expect you to know quite a lot about enthalpy here. All right. Let's just do this. Which of the following substances would obey Troughton's rules? Troughton's rule is the delta S of vaporization. We talked about that rule most closely. And so now they're talking about deviations from Troughton's rule. Troughton's rule is like it's around 87, 89 joules. But which of these would deviate most? You know, HF. What's this one? This one's called toluene or methanol. Explain your reasoning. Which one would be the most ordered liquid out of those? The most ordered liquid are going to have the strongest intermolecular attractions that hold it in position. So out of these 3, which one would be the most ordered liquid? Well, I think methanol is pretty well ordered because of the hydrogen bonding interactions there. You know, methanol is what we call miscible in water. It dissolves, you know, it's infinitely soluble in water because it's very water-like. It has hydrogen bonding interactions. And so you can, there's no solubility limit. You know, if there's no solubility limit, not only there's a solubility limit, the maximum, but this one's infinitely. But what has the strongest hydrogen bonding interactions? HF or methanol? You'd expect HF to have stronger hydrogen bonding interactions. It's more polar. So I'd say HF deviates the most. Followed by methanol would be a deviation, followed by toluene. Toluene would be pretty good with Troughton's rule. You know, toluene should obey it. But anyway, that's that rule. I can do that. Okay, let's move on here. So Delta S and delta H are easy calculations, right? And so we need to determine the ways to determine delta G. So ways to calculate. Obviously, we want to know all the ways to calculate delta G. Like delta H, what are all the ways of determining delta H? One way is you could do coffee cup calorimetry. Do you want to do coffee cup calorimetry? No. I prefer not to do any calorimetry. What's the easiest way of determining delta H? I think the easiest way of determining delta H is from delta H as a formation using Hess's law. So delta H of the reaction is equal to nu product. This is number of moles of product times delta H of formation of the product, which we get from appendix D, minus the sum of nu of the reactants times delta H. Actually, I don't need these parentheses. Get rid of those. I do need that parentheses there. But we're going to be restricted because appendix D is under standard conditions. These have to be under standard conditions too. That's the easiest. And delta S, the easiest way to determine delta S is just delta S is equal to S of the products, nu of the products times S of the products minus, this is the sum, sorry, minus the sum of nu of the reactants times S of the reactants. The easiest. So this is 1. However, this is not the easiest way. The easiest way is we use Hess's law. Hess's law works for energy.
Wait, what's that symbol after the sum symbol? Looks like VP.
It's nu, N-U. Which is the number of moles. Delta G of the reaction is equal to the sum of nu of the products, the number of moles, times delta G of formation. We have delta G's of formation too, of the products. This is not, note this is not G, the absolute. It gives free energy. This is delta G of formation. So we're just using formation reactants like we use for H. But this is restricted. In fact, both of these are restricted. Both of these have to be under standard conditions at 298 because delta H is going to be under standard conditions, and both of these have to be at 298 Kelvin because our delta, unless we look at other tables, but our appendix D table is only at 298 Kelvin. And so restricted to standard conditions at 298. And so we have to keep track of this. And so the way I'm going to keep track of it is like this. I'm going to just write a little temperature. That, there. And same thing here. This is going to be for the reaction at 298 Kelvin. The problem is a lot of reactions we don't do at 298. Most of them maybe we'll do at 298, but there are some that we aren't doing at 298 Kelvin. And so what if we're not at 298 Kelvin? Then there's a problem. So what I'm going to say is that these ones This is why thermodynamics is a pain. You have to keep track of this. And imagine, some people don't even want to keep track of units, let alone all these restrictions. What are the restrictions on delta H? What are the restrictions on delta G? Where is this calculation valid? And a lot of people don't want to even deal with these restrictions. But they end up using the wrong equation and get the wrong answer. So anyway, this is fairly straightforward. These are pretty simple calculations. And then we see delta G. Is it negative? Is it positive? Is it 0? And let's talk about the magnitude of delta G first. When we're looking at delta G's here, we see it like, minus 200, like kilojoules per mole or something like that. Minus 50 or 100, actually maybe minus 100, minus 50, 0, plus 50, plus 100, plus 200. These are quite spontaneous here. This is a large driving force. Here we're going to have more of an equilibrium type situation. Here we're going to have pretty much an NR type situation, no reaction type situation out here. And so we got to see, what's the range of delta G's that we typically see. And so the magnitude, we're going to look at this a little bit later. For right now, we're just looking, is it positive, negative, or 0? And then later on, we'll like to know, well, how positive, how negative is it? And there we'll need some kind of reference point, some anchor, to let us know, what's big, what's small in terms of delta G. But before we do that, let's go at temperatures, delta G at T not equal to 298 Kelvin. Then it appears we're stuck, right? If the temperature is not at 298 Kelvin, what do we do? This is what we're going to do. One, we do this. Delta G at T is equal to delta H at T minus T delta S at T. Do we have more data tables in Appendix D, ones that are not at 298 Kelvin? No, we're stuck here. So we aren't going to be able to determine this. Maybe we could get delta H. There are different ways of getting delta H, right? So we probably can get delta H at a temperature not equal to T. For example, delta H is equal to delta S over, or T delta S at phase transitions, that kind of stuff. There are other equations that we can do. But what we're going to do is we're going to say this. This is going to be approximately equal to delta H at 298 Kelvin minus T delta S at 298 Kelvin. So what we're saying here is that the delta H isn't going to change much. So let's look at vaporizing water. If we vaporize water at 298 Kelvin versus vaporize water at 300 Kelvin, is there much of a difference in delta H? No, you're taking liquid and you're vaporizing to the gas. So whether you do that at room temperature, or you do that at above room temperature, or you do that at higher temperatures, it's around the same, because you got to break the hydrogen bonding. So, just because there's more kinetic energy initially and more kinetic energy final, you still have to break the hydrogen bonds. That's going to cost you a certain amount of energy. So this is the argument for that. Of course, if there's some phase transition that's going to screw everything up, but as long as it's the same, then we're going to use this. And it's not going to be exact, but it's going to be pretty close. So we're going to use this to calculate delta G at temperatures other than 298, because here, for this temperature is a variable, and so we can put in whatever temperature we want. Correct? So this gives us a way of manipulating the driving force. The driving force can be changed with temperature. In fact, we can completely reverse the driving force with temperature for some reactions. So an example of this would be, let's say we go from H2O liquid to H2O gas. And we calculate delta G at 298 Kelvin. You know, even though some water will evaporate, most of it will stay liquid. And so delta G for this is going to equal delta H at 298 minus T delta S at 298. And so let's see how non-spontaneous this is under standard conditions. The standard conditions for this is 1 bar. Yeah. And so H2O gas to H2O liquid, let's calculate our delta H quickly. Our delta H is we're going from liquid to gas, it's vaporization. So it's going to be the product, 1 mole gas minus 241.8 minus the reactants. So it's going to be a minus minus, so it's going to be plus. And so this is going to be plus 44.0 kilojoules per mole. Delta H of vaporization water, 298 Kelvin. That's a familiar number. You've used that number in Chem 1A and Chem 4, wherever else. It's plus 44.0 kilojoules per mole. Is it cursor? We're just dealing with 1 mole here. So I'm just going to put 44.0 kilojoules. Minus T. T is 298 Kelvin. And then delta S at 298 Kelvin. Delta S at 298 Kelvin, let's take a look at the entropy. Here. The entropy is the 3rd column. So it's the gas minus liquid. 188.8 minus 69.91. So 188.8 minus 69.91. 118.89. That's 1 extra digit than I'm allowed. Okay, so this is going to be 298 times 118. Ran out of room here. Let me scroll this over. Let's see if I can find the curve again. 118.89 joules per Kelvin. Okay, then I'm going to have to convert either kilojoules into joules or joules into kilojoules. I'm going to convert kilojoules into joules. So I'm just going to go 44,000 joules minus 298 times 118.89. I get this. I get 8,570 joules, which is equal to 8.57 kilojoules. Why isn't this scrolling down? Which we say is non-spontaneous. And therefore, liquid water is the favorite phrase at 298 Kelvin. And what I'm going to do is I'm going to say this. At what temperature will this become spontaneous? So what we want is we want the delta G to go from positive to 0 to negative. So I'm going to try to calculate at what temperature will delta G become 0, because that's the transition between non-spontaneous to spontaneous. And so we got to go through 0. So 0 is at the borderline. So what I'm going to do is I'm going to set my delta G equal to 0. And this is going to equal delta H minus T delta S. Now this is delta G at some temperature T. We don't even know what that temperature T is yet. But what we're going to do is we're going to assume that this is close enough to delta H at 298 minus T delta S at 298. And these are under standard conditions. Now the standard conditions for appendix D is bar, 1 bar. 1 bar pressure. So we set that equal to 0. That means delta H naught at 298 is going to equal T delta S naught at 298. So I'm going to take, the T is going to be delta H naught divided by delta S naught. Both of these are 298. This is approximation. Right? And our delta H we just calculated, that's 44,000 joules. And our delta S is 118.89 joules per Kelvin. And so I'm going to take 44,000 divided by 118.89. $370.0. Let's just do that, 08, whatever. We'll just say 370 Kelvin. Minus 273.15, 96.93. Do you know the boiling point of water at 1 bar? I know the boiling point of water at 1 atmosphere. What is the boiling point of water at 1 atmosphere? 100 degrees C, 373 Kelvin. This is boiling. But is a bar smaller than an atmosphere, or is a bar bigger than an atmosphere? It's a little bit smaller. Since the bar is a little bit smaller, the boiling point of water under standard conditions is a little bit lower than 100 degrees C. Is it this much lower? Probably not this much lower. We could calculate it using, remember the Clausius-Clapeyron equation from Chem 1A? We could use the Clausius-Clapeyron equation to calculate the boiling point, different pressures. But it's probably not this low. It's probably off a little bit. But this is the boiling point of water under standard conditions, according to our thermodynamic calculation. We're off a little bit, though, it seems like. But it's okay because we're not using the proper delta H and proper delta S. We expect something closer to 100 degrees, but not exactly 100 degrees. I wish they would just go back to the atmosphere, because then we could see what it is. Or maybe it's not that big of a difference anyway. All right, so this is the one application of this. We can change the driving force. We can make water boil spontaneously by just changing the temperature. This works because this is the scenario where delta H is, remember delta H is positive here. That's a no-go. So delta H is positive, that's a no-go. However, delta S is positive too, because we're going from liquid to gas. This is a go. So this is a no-go, that's a go, and therefore the temperature, this is spontaneous at high temperature. Spontaneous at high temperature scenario. All right, so that's the first thing. Delta G at temperatures other than 298. Because delta G is heavily influenced by temperature, whereas delta H and delta S are not. Heavily dependent on temperature. Therefore, delta G at temperature T under standard conditions is not equal to nu P delta G of formation at 298 under standard conditions of the products minus nu R delta G of formation, standard delta G of formation of the reactants. This equation fails. Even though people in Chem 1B try to apply this, it fails. It's not equal to this. The next thing we're going to look at is, do we always want to be working under standard conditions? No. What if I want to go back to 1 atmosphere? I don't want to do it at 1 bar. I'd like, water to boil at 100 degrees C. I don't like water to boil at lower than 100 degrees C. And plus, 1 atmosphere is the average pressure at sea level at the equator. And so I'd rather do that. Whereas 1 bar is not. 1 bar has a physics definition, not something that's based on observation. And so we're going to do delta G under non-standard conditions. There's a long derivation in the book. I'm not going to go through the long derivation in the book. But delta G under non-standard conditions, all we do is we take our delta G under standard conditions and then correct it. So this is delta G under non-standard conditions at temperature T is equal to delta G under standard conditions at temperature T with a correction. And so what is the correction that we're going to apply to this? And the correction that we're going to apply to this is RT ln of Q. This is a correction. Where Q is the reaction quotient. That is, it's the activity of the products raised to whatever power over the activity of the reactants. And so, to whatever power. So this is not terrible to deal with. So it depends on the product to reactant ratio that we have. That's going to alter the driving force totally. If the reaction, actually I'm out of time. But I'll stop here and then we'll continue this. I'm almost done with this chapter.
When do we not have class? Next week?
I have to leave, next week I have to leave on, I'll be out Wednesday and Thursday and Monday. So what I'm going to do is I'm going to post some videos for Wednesday. Wednesday's a lab day, Monday's a lab day. So the videos I'm going to post are going to be, I can talk about it tomorrow too, are going to be talking about the current lab. Monday. I could